Hello again, guys, and welcome back. We're going to be talking about electron configurations and orbital diagrams today. So, AKA, this is how you send mail to electrons. Who'd have ever thought that you would have needed to do this? Not really. We don't send mail to electrons. However, it's important to know essentially what we would call their address, which is an electron configuration at its most basic. So, what is an electron configuration other than a atom's address? Electron configurations show how electrons are distributed around an atom. So we have that image in our mind of a nucleus, and we have electrons around it in their own little area, like that. Well, just so you know, they are distributed in a very specific manner around it. They're not just in a random cloud, they have their areas. And we have to be able to talk about these areas that they're in, which relates to bonding later on. So this usually contains the following information. It will talk about the energy level, the orbital type, and the number of electrons that go into the orbital. So an example of this is the ground state of sulfur. So it's 1s2, 2s2, 2p6, 3s2, 3p4. All of these numbers will make sense once we go through them. This is to kind of give you an idea of what this is going to look like once we're finished. So first thing we have to start off with is how we ascend energy levels when we're talking about all of this. And we use the Aufbaum mnemonic for this. And it literally tells us the order in which to fill energy levels and their corresponding orbitals as we go up. So it may not make sense now, but we usually we go 1s2, and we go 2s2 into the next energy level. And then we go 2p6, we go over from left to right, and then we're going to go up into 3s2. We're going to go to 3p6, and then we're going to follow that arrow again up into 4s2. And this is where it gets a little bit weird because we go over to 4p6 again. But you see this down here? We don't go into the 4p6 until after we go back into this. So it usually goes 4s2, 3d10, 4p6. And this is why we use the mnemonic, because remembering that we have to go back down in energy levels tends to throw us off a little bit. More about that in a little bit. It has a very specific reason. We don't just do it randomly. First off, let's talk about what all of the letters mean and what all of those numbers actually mean too. So this has its basis on the periodic table, as you can see here. So everything that's coded in the dark purple is the S orbital. Everything in the dark blue is a D orbital. The lighter pink purple is the P orbital, and then the light blue is the F orbital. Now these orbitals have different shapes and they exist in different regions of space. And all you really need to know is that they exist. You don't need to know what they look like right now. That's something for later if you want to get into other varieties of chemistry and more advanced chemistry. But for now, we just need to know this is how they go. And we usually fill S to P, D to F. Once we go through this, we're going to add them in that order as we go through. Now, when we talk about energy levels, we're actually talking about going down the periodic table over here. This is our first energy level going this direction, second energy level, third energy level, fourth energy level, fifth, sixth, and seventh. And that's where we end. And these sections of elements get put in different places. So like this is where our F orbital block goes. And it was an insertion. We can't really expand the periodic table out to fit what we need it to, so we kind of just put it on the side. But they all do fit into this energy level progression as we go down the periodic table. It always goes this way too. There's not anything that's going to differentiate that's going to change as we go through this. It's always going to do that. And then we also have to be able to recognize what group our element is in. So we have our periods, which are the energy levels, and they go this way. okay? These, like right here, these are groups. And in the old numbering system for the groups, it went 1A, 2A, 3B, 4B, 5B, 6B, 7B, so on and so forth. That's the old way. We don't use that anymore. You only need to know the normal way that we do things now, which is in green here. So we just label them as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, on to 17. It's way simpler. So be thankful that that's how we number them. We don't number them the old way anymore. So just be aware that we do number these things, and we will refer to the group number and to the period number usually by its energy level that it's going to be part of, either 1 through 7. Okay, so this is where we get into the orbitals. Well, you don't need to know the shape or anything. We do need to know how these fit in energy-wise. So down at the bottom, the orbital that is lowest in energy, where electrons are just they're gonna fill it right away, because we aim for stability. Always keep that in mind when you're doing these things. We always aim for stability. So whatever is lowest in energy. Okay, so we start with the 1s, we go to 2s, it's the next highest in energy, and then we go to the 2p. 2p has 3 orbitals, which, if I didn't mention before, is why we have these numbers in parentheses to the side of these orbitals. Each orbital has a characteristic number of separate orbitals within it. So we'll have 1s orbital, 3p orbitals, 5 ds, 7 f's. That's how we fill. So we're going to go 1s, 2s, 2p to its 3 orbitals, and then we're going to go to 3s, and then we're going to go to 3p, then we're going to go to 4s, and then because the 3d orbitals are lower in energy than the 4p orbitals, yet higher than the pre-designated orbitals we've already gone through, they will be filled next. This is why on the Aufbaum mnemonic, which was back here, we show the 4s going straight over to the 3d and not straight to the 4p. We have to fill the 3d orbitals first because they're lower in energy than the p orbitals, the 4p orbitals. And this is true of any of them. Once you get into the 5th energy level, we're also going to drop back down. 6th, we drop back down. And then we're actually going to be adding on another one eventually. We're going to be adding on the f orbitals like that as well. But that makes sense. That's why we do that. To also give you an idea, we add on the 1s, and then we add on the 2s, and then we go to the 2p, because across here, if you notice, these are all s orbitals. This is all s orbital. We fill this direction like this. This is 1s1, 1s2, and this is the second energy level. So we're going to fill across the entire energy level first before we move down, which means that we fill our 2s right here, and then we're going to fill all of our 2p. And then we get to the 3rd energy level and we fill across. Okay. But when we get to here is where it gets whacked. So we're on the 4th energy level. We're going to fill the 4s. And then these right here are 3D. They're weird because they're higher in energy than the rest of their buddies up here in the 3rd energy level, but they're lower in energy than the 4p orbitals here. So that's the basis behind this. But always think that on the periodic table, we are filling these things. We're filling this graphic in this direction in a way that makes sense as to what the periodic table looks like. Now, because there weren't enough rules before about like the Aufbaum mnemonic and all of that, there are rules for filling the orbitals. I've mentioned a couple of them. So first off is the Aufbau principle. Electrons are added to the lowest energy levels first. We've talked about this. This is why this goes on. We go 1s, 2s, 2p, 3s, 3p, 4s, so on and so forth. We add to the lowest energy levels first. We fill that entire energy level, and then we move up to the next one. It's the basic rules for this. Now, second is something called the Pauli exclusion principle, where it says that only 2 electrons are in an orbital and they must have opposite spins. What does this mean? Well, an electron can have a spin of plus or minus 1/2. Seems weird. They do have spins like that, but this means that this rule applies now. So because we want an overall spin of, we want the spins to cancel out inside of each of the orbitals, and we literally want them to be spinning in opposite directions so that they have, I guess, space away from each other, equal repulsion and attraction with the nucleus. We only want 2 electrons. We want them to have maximum space, as much as they can get, since they will repel each other. And they have to have those opposite spins for the same reason. And we just know this when we go and we're filling or energy level diagrams and orbital diagrams. You'll see why this matters, but we have to just be cognizant of it. Now, the last rule that you need to keep in mind when we move on from this is Hund's rule, which says that electrons occupy orbitals so that the number of unpaired electrons is maxed before any are paired. It seems kind of confusing initially. I'm actually going to go on and demonstrate this to you so that you know what this looks like. It's easier once you apply it to an actual example. So with the Aufbau principle, it is simply this energy diagram right here. We are going to fill these in such a way that we fill the lowest energy first, the lowest energy levels first as we move up. So you don't fill all of the s orbitals first. No, don't do that. You fill 1s, 2s, then 2p because it's next in line. You move back over to 3s because it's also next in line energy-wise. Don't fill it any differently. Otherwise, you will confuse yourself and you will put electrons in the wrong place. Okay, Pauli exclusion principle. What does this look like? What do? It looks like this. See these little things? This is 1 electron. This is also 1 electron. We get the picture. Rule is 2 electrons per orbital, and they must have opposite spins. The arrow going up or the arrow going down means opposite spin. So you can assume if it's going up, maybe this is the one that has the plus 1/2 spin. Maybe this is the one that has the minus 1/2 spin. Either way, we know they have opposite spins, which is good. So that means that when we filled this, we did this and this, and oh, look at this, they all fit. And because we didn't have another electron to pair with this dude right here, he's just going to be hanging out all by his lonesome in that orbital, which is fine. Atoms do that all the time. What not to do is this. Like, this pains me right now to look at this. When I wrote this, it pained me to do it, because electrons will not have the same spin in their orbital. And do not ever put 3 electrons and attempt to include them in the same orbital. That doesn't work. There's only ever 2 electrons in an orbital. Remember it. Remember, it's an important rule. Okay, so last one is Hund's rule. What to do is this. See, we fill this one and this one, this one and this one, and then we distribute the last 3 electrons to each of the p orbitals. You cannot do these ones like this and then distribute 2 to one orbital, 1 to the next, and then leave the last one open. You can't. Why? This actually has an energetic basis. What do I mean by that? I mean that this is more stable. This is much less stable. Because what it means is we're sticking 2 electrons into an orbital together. We're sticking 1 other electron into another orbital by itself, and then we're leaving a 3rd orbital empty when we don't have to. We've got 2 electrons that are in close quarters, another electron that's by itself in an empty orbital. This just does not work. The electrons do not want to be next to each other if they don't have to be. We want them to have as much room as possible because they will repel each other. So this is why what you do is you split those 3 electrons with 1 electron per orbital. What this does is this gives them maximum space in their orbitals before we start filling them. And it makes sure that they're happy with their life. They have the room to move around, and they can repel each other in such a way that doesn't put more stress on the system. Okay, so now an example, an orbital diagram is different from an energy level diagram. We are only trying to look at the dispersion of electrons into the different orbitals. Well, we do care about how this looks energetically going across from left to right. It's not the same as an energy level diagram where we are actively displaying energy on an axis and then drawing stuff in relation to it. This one is more a visual for us to recognize how we place electrons. So an example here is I'm going to do this with fluorine quick. So fluorine has an atomic number of 9 protons. It's a neutral atom. We've gone over this before. Therefore, it has 9 electrons. Okay, so let's do this. First off, we start at the lowest energy level, which is the first energy level in its s orbital. And we're going to put 1 electron, and then we're going to fill it because there's only 1 orbital with the other electron of opposite spin. Then we're going to move up to the 2s orbital. We're going to put 1 electron because there's only 1 orbital. We're going to put an electron of opposite spin. Now we move into the 2p orbitals. Okay, so we still have 5 electrons when we get to this point because we have 1, 2, 3, 4 here, 2 here, 2 here. I minus 4 is 5. There you go. So we have 5 electrons left, which we can use to fill the 2p orbitals. So we're going to start this way. We're going to put an electron into each of the p orbitals. We've used 3. We have 2 left. Okay, so now we're going to pair them. So we put an electron of opposite spin in that first orbital. We put an electron of opposite spin in the second orbital, and we leave the last one open because we are out of electrons. So fluorine has 1 unpaired electron, and the rest of its orbitals are filled. We have 9 electrons shown here, which means it's a neutral atom, and we have all of the energy levels filled like they should be. That, my friends, is how you fill an orbital diagram. Okay, so now you're going to ask me, why do electron configurations matter to this? We've been talking about energy level diagrams and how to fill them and doing orbital diagrams. Why do we care? Because electron configurations are a miniaturized version of essentially how to fill these diagrams. And while it doesn't necessarily show us the spin of the electrons, and it doesn't show us exactly the number of orbitals that we're going to have and how we fill each of those orbitals with electrons, it implies them and it fits with them, and we'll see that. So like with helium, it's in the upper left-hand corner of the periodic table, the very first element in the 1s orbital. It's going to have a designation of 1s1. This 1 right here indicates the number of electrons in the orbital, okay, in that energy level. So we can move over to helium, which is on the other side of the periodic table, but it's still in the first energy level, and it's still with an s orbital, and it's going to be 1s2 because it has 2 electrons in the s orbital, which means it's now full. An s orbital has 1 orbital, it can contain 2 electrons, only takes 2. Now we move on to lithium. So we have the first energy level, second energy level. It only has one electron in that 2s orbital right now, so we designate it with a 1. Okay? And it's filled that 1s orbital, and we're going to write it in that order. Now we move on to beryllium. It's in the second group of the periodic table. It's labeled number 2. It has a filled 1s orbital and a filled 2s orbital, hence the designation of 2. There are 2 electrons in that s orbital. Okay, so now we move on to boron, which is now into the next chunk with the rest of all of the metalloids and the nonmetals. And it's filled its 1s orbital, its 2s orbital, and it has begun to fill its 2p orbitals. It only has 1 electron to do this with, though, so we're going to put it as a designation of 2p1. Okay, now with carbon, next over, 1s2, 2s2, 2p2. It has 2 electrons that can fill that set of p orbitals. Nitrogen, 1s2, 2s2, 2p3, 3 electrons to fill. Oxygen is 1s2, 2s2, 2p4. Now, as a designation for you, S can only ever have 2. P can go up to 6 because we have 3 orbitals with 2 electrons each. And for the eventually, when you get to the d orbitals, they can have 10 because you have 5 orbitals with the 2 electrons each. And then F can have 14 because you have 7 orbitals. And it's always a designation. Each orbital has 2 electrons. It's the number of orbitals that changes. Okay, so that's how you write an electron configuration. You have to designate the number of electrons that have filled that energy level and its orbital, and you move on. And when you run out of electrons, you just fill it in that manner. You move up your energy levels, you move up your designated orbitals, and you fill them. You write the numbers in the superscript. Now, a note, shorthand, the last noble gas symbol followed by the rest of the row can be used to show a element's place. So I have oxygen right here for you. I also wrote its shorthand configuration, which honestly isn't that short. It doesn't really have need for a shorthand configuration yet. But either way, because helium is the last noble gas to be on the periodic table before oxygen, we can write it in brackets here. And then we're just going to pick up again at the energy level that oxygen sits on. So it starts at the second energy level. So we're going to start off with 2s2, 2p4, and that is how you write the shorthand version for any elements in the periodic table. So you're going to say, why does shorthand matter? Guys, shorthand matters because we don't want to write this. This is the electron configuration for element 114 on the periodic table. You can look it up. It's not cool because you have to write out every single energy level, every single orbital, and all of the electrons that are in that orbital. It doesn't necessarily take a long time, but it's really annoying. And it's a lot of writing, and you tend to get a little bit mixed up because, you know, when you get to here, you're dropping energy levels to be able to designate that you have reached a point where the energy of this set of orbitals is less than it could be here. So shorthand is necessary if you don't want to write stuff like this. This is very important. Now, for practice, though, if we want to write this in shorthand, we know if we come up here, we have 1s2, 2s2, 2p6, so on and so forth. We need to find the next time that the s orbital shows up, which is right here in this line. Guess what? All of this can be represented by putting a noble gas into brackets. What a thing. Believe it or not, that noble gas is in fact radon. So what does shorthand look like? We're going to use brackets. We're going to put radon into those brackets. And then we're going to write what we just wrote. which is 7s2, 5f14. So we dropped those 2 energy levels because the f orbital happens to be lower in energy than both the d orbitals that are going to come up and the p orbitals of the same energy level as those s orbitals. It's a little bit weird. If you have questions, ask Mrs. Merriam if you don't understand why we're going to do this. But we do 7s2, 5f14, and then we're going to go 6d, and it should be 6d10, 7p2. It's a heck of a lot shorter than doing this longhand. So remember, shorthand is very important. Okay, so now to give you an idea, we've done a orbital diagram. I've shown you both longhand and shorthand for writing out the electron configurations of elements. Now we're going to do an energy level diagram. Now for practice, I'm also going to write out the electron configuration of manganese, which is one of the transition metal elements in the D block of the periodic table, which is that main center block that begins at scandium and then ends at zinc and then goes down. So we know, I'm going to write out the full version of this since we're going to be starting down here at the 1s orbital. Okay, so it's going to be 1s2 because it has all of its 1s orbital filled. 2s2, all of the 2s orbital is filled. 2p6, same reason. And then we're going to move down to the next energy level. So it's 3s2. Because the 3d orbitals are higher in energy and they don't actually show up on the periodic table with the third energy level group quite yet, we're not going to worry about them. So we go to 3p6 to show that we have all of our p orbitals filled. And now we're going to make it into our 4th energy level, which is 4s2. It's filled the entirety of the s orbital in the 4th energy level. And then now we're going to worry about filling the 3d orbital. Okay, so this is where we're going to count over for the number of electrons that are going to be in that. So we have scandium first, then we have titanium, vanadium, chromium, and manganese. And this will be easier if you guys are looking at a periodic table while I'm doing this, because we're looking at the D block right now. And so we count over, and once we reach manganese, we are 5 elements into the D block, which means that this should have 5 electrons in the D orbitals so far, which means we're going to put 3d 5. We have half the number of electrons that can exist in a set of d orbitals right now in the 3rd energy level. So this is the electron configuration for manganese. Shorthand, just to let you guys know, we're going to go back to the most recent noble gas, which happens to be argon. We're going to put it in brackets, and then we're going to write out the last section of this. So it's just 4s2, 3d5. All right, so now we know what it looks like to write out the electron configuration. We know where the electrons are. We know what the energy levels they're in. We know the order in which they fill. Let's worry about an energy level diagram. So this is what it's going to look like when you draw it out. This is energy over on this axis over here. And our orbitals are split apart so that we show the increase in energy from one to the next, so on and so forth. So we know that we're filling the lowest energy level orbital first, moving up, as is taught by Aufbaum's rule. Okay, so we know that that's how we're going to start this. So we're going to fill our 1s orbital. Remember Pauli exclusion principle, 2 electrons of opposite spin in the orbital. Bam, we've got that. We're going to do it with the 2s. Same thing. Okay, Hund's rule kicks in when we get to the 2p orbitals yet again. So we're going to fill each of these with an electron. We're going to go back and we're going to pair them with an electron of opposite spin for a max of 2 electrons in each orbital. Pauli exclusion principle again. We're going to do the 3s orbital now. Pretty simple. We're going to repeat the same thing with the 3p orbital. So that's full. Now we're onto the 4s orbital. It's also full according to this over here. So we're going to put 2 electrons in of opposite spin. All right, this is where it gets a little interesting. So we only have 5 electrons in the d orbitals. There are 5 d orbitals. What does this mean? It means that we have to distribute these electrons one by one into each of the orbitals before they can be paired. But if we know that there are 5 orbitals, 5 electrons, this means we are going to have 1 electron per d orbital. So the d orbitals are half full. A fun fact, manganese is one of the most stable elements in the transition elements as it sits as a neutral atom right now, because it has an electron each one of its orbitals, which can help stabilize it. So it's full. We don't have to worry about the 4p orbitals. We haven't reached them yet. We haven't filled the 3d. So this is what the energy level diagram of manganese is going to look like. And this is, let me repeat, for the neutral atom. Were we doing this as an ion, it would be a little bit different because manganese is a transition metal. Transition metals will normally lose their electrons and become positively charged, which means that it may not always have 5 electrons to fill those d orbitals. It may actually have less. So just keep that in mind when you're doing electron configurations for ions, which you eventually will do if you keep going in chemistry. They're not much more complicated. You just have to talk about the fact that they may lose or gain electrons and therefore may fill or empty out orbitals. Okay, so that was a lot. And I get that some of it might be confusing. You may be like, why the heck do we jump down 2 energy level numbers when we're going to be filling the F orbitals? And why the heck aren't they part of the periodic table? Those are great questions. I suggest you pose them to Mrs. Merriam. She's probably a little bit better equipped to answer them. Other than that, I wanted to leave you guys with a funny joke to kind of just, mellow you out after that onslaught of information. So I hope you appreciate this as much as I do. I began the whole session with talking about how electron configurations are literally the address of electrons because it designates the spot on which they exist on the periodic table. While an atomic number can do the same thing, an electron configuration does it better because it not only tells you the energy level that it's in, so the period that it's in, the row that it's in, it also tells you the number of electrons is going to be there, and it tells you which orbital it ends with, which also tells you which region of the periodic table that it's in. So it's pretty awesome. And I hope you appreciate this. Be cognizant of the fact that it was the electron that delivered this letter. Anyways, with that, if you guys have questions, yet again, ask Mrs. Merriam. She'll be able to answer them for you. If you feel that she can't, look it up on the internet and read about it somewhere if you are that involved. Otherwise, thanks for listening and have a great day, guys.